the purpose of the through the techniques of quantum integrability and the theory of symmetric functions. That's what's behind it. Okay, so a comment on complexity is that actually, even though these coefficients are all known and well studied, not everything is known about the complexity of computing them. So in the case of the characters of the symmetric group, this problem is conjectured but not known to be gap P complete. This is relatively recent work from the last 2 or 3 years. More is known about these other coefficients that appear, these Kostka numbers and these Klopstock the Richardson coefficients. Those are known to be sharply complete. So you see that already the simplest spin chain contains quite non-trivial data, which is hard to compute. Okay, so let me take a step back and give you a little bit of motivation how I think about this problem and what drew me to these kind of questions. So you could say that there are perhaps 2 approaches to quantum algorithms. So you could say that if you consider kind of the space of all the computational problems we would like to solve, encapsulated here, and then we have the top, and then at the bottom we have quantum systems. And often a way of reasoning is to a way of finding quantum algorithms for solving problems of interest, or call it a top-down approach, where you start with a problem that you want to solve, and you try to fit it into a quantum mechanical system. So famous examples of this are, of course, factoring, discrete log, and many others. Now, the question that naturally arises here is, okay, so you have a problem that you want to solve, that you're interested in solving, but you really have no idea if you can kind of formulate it, if it plays naturally with a quantum mechanical system. And so it's hard to say that you can actually get a quantum advantage by doing this, because these problems in principle have nothing to do with quantum mechanics. So even though for these problems we do believe you have a quantum advantage, it is difficult to see that because the original formulation has nothing to do with quantum mechanics. So here I want to ask a different question, which is what do quantum mechanical systems naturally want to compute in some sense? And I guess part of the talk has to do with understanding what I mean by want to compute. But yeah, to Victor's comment, then you could say, for example, that free bosons want to compute permanence and free fermions want to compute determinants. Okay? So these are very simple, non-interacting quantum mechanical systems, and this is what is encoded. It's not observables. So I will call a bottom-up approach to identifying problems with potential quantum advantages to look at quantum systems, understand what it is that they want to compute, and then hopefully see that the quantum mechanical effects which are relevant to describing that problem kind of remain classically non-similar. Okay, so in this talk I want to talk about spin chains, which are, I guess, the other kind of canonical simple system of quantum analog system. Okay, so if you think of kind of the landscape of quantum systems, you can divide this into unstructured problems, structured problems, meaning unstructured Hamiltonians, and structured Hamiltonians, the ones that have lots of symmetries and one have very little symmetry. So usually the kind of Hamiltonians we would like to simulate for purposes of chemistry or material science, if they're not toy models, they would typically not be very structured Hamiltonians. Whereas here on this end, you would have Hamiltonians that typically appear in the mathematical physics literature. And if you're so that's kind of this direction from less structured to more structured. And then in this dimension, I'm showing systems which are less interacting or strongly weakly coupled or weakly correlated and more strongly correlated. And so you would find in this area of structured systems, you would find, for example, 2 examples are supersymmetric systems. Those have a symmetry that relates bosonic degrees of freedom to bosonic degrees of freedom. Integrable systems that have much larger number of symmetries. In some sense, they're more structured, and they can be less or more interacting or correlated depending on the system that you consider. There's also an overlap between these models. And I guess the kind of big picture question you'd like to ask is how does this line of quantum advantage cross transversely across the space? So today I want to tell you about spin chains that fall in the category of quantum integrable systems. And here I do them slightly outside of the area of quantum advantage, although it's not entirely clear. But this is not known. It's not one of the claims of this lecture, whether this is inside or outside. The point is to identify this physical system and understand that it has interesting computational properties, and then we need to understand which side exactly it applies. As I said, these problems are sharply hard or gappy hard. So exact solutions will not be feasible classically or quantumly, but here I'm referring to approximations or sampling complexities associated with these problems. Okay, so today I'm going to focus on this level here, characters, Kostka numbers, and obscuring coefficients. But there are a few other examples and many other examples. And you can see that these other examples become more interacting or more complex. And so if you fail to find quantum advantage, in this case, it's quite considerable, but you could get these more interactive systems. Okay, so I'm going to get back to this picture by the end of the talk, but so here's the outline. So I'll first tell you about quantum spin chains, particularly the XX spin chain and its properties of quantum integrability. Then I'll switch gears and I'll tell you about the theory of symmetric functions, which in principle has nothing to do with quantum mechanics or anything. And then I'm going to quantize the theory of symmetric functions. I'll explain what this means and how this relates to the study of spin chains. Okay, so this will give an organizing principle to understand what it is that quantum spin chains want to do. Okay, and then I'll finally discuss a program of understanding the complexity of these problems and developing quantum algorithms. Okay, any questions so far? All right, so quantum spin chains. So let's consider the simplest spin chain, the XX spin chain. So consider 1D chain of n sides, and consider the sector we have k spin down. This chain may be open or closed, so I'm going to consider mostly an open chain here. And the Hamiltonian of the XX model is just given by this. So this XX refers to the fact that this coefficient and this coefficient are said to be equal. But there's an overall rescaling of the Hamiltonian that sets them to 1. So as you probably know, this Hamiltonian is exactly solvable. You can find not only the ground state, but the entire spectrum of the Hamiltonian by using the Jordan-Wigner transformation, running it in terms of free fermions, and then rotating the fermions to find the completely diagonalized Hamiltonian. So under the Jordan-Wigner mapping, spin up will go to 0 fermions, and spin down will go to 1 fermion. And the Hamiltonian basically just takes a fermion at one side and makes it hop by 1 unit to the next side. So that's very simple Hamiltonian. And I claim that even though this Hamiltonian is very simple and the ground state computes nothing interesting, there are other observables in the systems which capture all this data. Okay, so where do these other observables come from? So they come from this formalism of Bethe, called the algebraic Bethe formalism in particular, that reveals that these Heisenberg spin chains, and in particular XX spin chain, is an example of a quantum integrable system. So concretely what this means in this case is that in addition to the Hamiltonian, there are other operators, which we're going to call currents, which are simply given by this. So these are just operators which make a fermion hop k units in superposition. So the Hamiltonian would be the case of k for 1. And now the claim is that all these operators exist, they're going to be defined, they act on that spin chain in a non-trivial way, and furthermore, they all commute with one another. Okay? So this is kind of the non-trivial part of the statement. These operators exist, and they all commute. So, because for j and k equal to 1, this contains a Hamiltonian, all these currents, higher order currents, they're all symmetries of the system. Okay? So the Hamiltonian is sitting on the bottom of a whole tower of operators, which are all symmetries. And the statement that the system is quantum integrable means that this tower of operators, this whole package of operators, is maximal. So it's a maximal set of symmetries that the system has. So any symmetry, you should be able to write in a linear combination of these currents.
Can I just ask, are I and K sites or like single particle wave numbers?
They're sites.
Thank you.
And the J state commute with the Hamiltonian as well.
Yes.
J0 is the Hamiltonian.
Yeah, J1 is the Hamiltonian.
Yeah.
Well, rather it's like, yeah. Okay, so the statement that this is a quantum integrable system is that all these symmetries commute and it's a maximal set. So if you wanted to derive this from first principles, you would have to apply this Bethe formalism, which is something that actually Feynman wanted to learn. Unfortunately, he didn't have time to because this is a picture of Feynman's last blackboard in 1988. And you can see here Bethe ansatz is one of the things that you wanted to understand. So I'm not going to explain it to you today. It's a complicated story. But for the case of the XX spin chain, you can just check by, use the anti-commutation relations of the A's with the daggers. They're just canonical fermionic anti-commutation relations that indeed all these operators commute. Okay, so I'm not going to go into details of the Bethe ansatz, but just the Bethe ansatz implies that these operators exist and have these properties. And I'm going to construct out of these basic building blocks, the Bethe operators, I'm going to construct more general operators. So consider a set of integers, lambda I. And for each of those lambda i's, I associate a current. The current, so this is J, lambda 1 is an integer, so then I take the product over all these currents. Okay, so this is just a definition of what J lambda is. Now, because these J hats commute, then the ordering here doesn't matter. Maybe these are quantum operators because they commute, the order doesn't matter. And so I can always order my sequence of integers in a kind of decreasing order like this. So that means that this operator J hat lambda is represented by a partition of n. Okay, so where the first row is the number of boxes in the first row is lambda 1, the second is lambda 2, and so on. Okay, so the only thing that matters is the number of boxes in each row. Okay, so to each partition, we can associate a current or a product of currents and just kind of call it a current. Okay, so the statement is that currents, which are symmetries of the XX spin chain, are labeled by partitions. That's the first claim. The second claim is that computational basis states are also labeled by partitions. And one way to see that is as follows. So consider a partition that is given by this J here, and consider a box which is big enough to include this partition. We're going to call the height K and the width n minus K. Okay, so consider the set of all partitions that fit inside a box of this size. Okay. And now, instead of describing the partition by how many boxes are in the first row and the second and so on, consider an alternative description which is given simply by this kind of bounding path that defines the shape of the partition. Now, to each of the, so every time I move up, I can associate a 1, and every time I move to the right, I can associate a 0. Okay. So this way, you see that the length of the path is n, because you move k steps up and n minus k to the right. So the total length of this string is n, and the Hamming weight is k, because every time you move up, you put a 1. So in other words, all the set of partitions that fit inside a box of this size are labeled by all n-bit strings of Hamming weight k. So that's the map between partitions and computational basis states. I'm going to interpret these as being fermionic states. Okay, so this is anti-symmetrized. And I'm going to call this the staircase. Well, it's called in the literature the staircase representation. Okay. It goes by different names. Okay, so this is one way to see that actually the counting works. So the number of partitions that fit inside this box is given by n choose k, which is equal to the number of states. Okay, so now there's a preferred state in this description, which is the empty partition. So the empty partition is where you go k units up and then n minus k to the right. So that means you have so that corresponds to this state, 1 to the k and then 0 n minus k. This corresponds to the empty partition. I'm gonna call it the vacuum. Okay. So if you're like a chemist, you will call this the Hartree-Fock state, where all the fermions are occupying the lowest orbitals, probably the lowest state. Okay, now the currents that I showed you before, they preserve fermion number. And so if I act on a partition that fits inside this box, then because if it preserves fermion number, which is k, then you're going to get, again, a linear combination of states which fit inside this box. Okay. And so let's just see experimentally how, what you get. And my claim is that if you act with these currents on this vacuum state, what you're going to get as amplitudes are going to be the characters of the symmetric group K. So remember, K is the number of spins down or the number of fermions that you started with. Okay, so let me just briefly remind you how do you define the characters. So first of all, irreducible representations of the symmetric group, which should be SK1, SK, are labeled by, let's call it SD. SD are labeled by partitions lambda of D. And what is a character? A character is, so you take a given matrix representation specified by lambda, irreducible, you evaluate it on an element in the conjugacy class, which is also specified by partitions of D. So both irreps and conjugacy classes are specified by partitions. So this is a matrix, you take the trace, this is a number called a character. That depends only on the conjugacy class of the element. Okay, so for example, so one comment is that if you take the empty partition here, corresponding to the trivial representation, this gives the trace of the identity, which just gives you the dimension of the representation. Okay, so let's do this for S3. So for S3, you have three partitions of three, which are these three here. So these label conjugacy classes here, and here these label irreps. So this representation, which is write like this, one cube, this just means there's one box in the first row, the second box, the third row, and so on. So this is the trivial element. Okay. And so you can see here that they are the dimensions of the three representations, three reps, and with dimension 1, 2, and 1. Okay. And so that the dimensions are given by the last column, and the other numbers are the traces and the other elements, not the identities. Okay. And notice that they're always integers, and they can be positive or negative integers or 0. So this is a character table for S3. Okay, so now consider the spin chain or fermion chain. I'm going to set K equal to 3 because I'm interested in S3. And I'm going to choose a number of sides to be at least twice as much as that. But you see later why I have to do that. But basically, when I start moving all the fermions to the right, and I want to have enough space to do all my computations. You can choose n to be at least bigger or equal to 2K, and then that's enough space. Okay, so my reference state, my vacuum state is 111,000. That's the empty partition. And if you count the total number of states, it'll be 20 states. So it's just. Okay, now let's take one of these currents, J3, for example, represented by this. So remember, J3 is just something that takes each fermion and makes it hot by 3 units in superposition. Okay. So you see, if I act with this this operator on this state, you can either take the last one and move it 3 units to the right, and you get 110010. If you rewrite that in terms of partition, you're going to get this partition here. The person here. So J3 basically creates a row with 3 boxes, okay, acting on the vacuum. Okay. Now, if it carries the second one, 3 units, then it has to hop over one of the ones. You're going to pick up a minus sign, and you can get 10101, and that partition corresponds to this because it's 10101. Okay, and similarly the last one. Okay, so you get these numbers. Now, what about if you act with the current associated to this partition? So remember that to each partition you associate a current that is given by the first box times the second, the first row times the second row. So this is J2 times J1, or it doesn't matter. Okay. So I first act with J2 and then I act with J1, and you just do the algebra, and you'll find there's some cancellations here, and you get these numbers. And if you do this for this other partition, you get these numbers. And if you compare it to the character table of S3, you find these numbers exactly match. It's kind of look miraculous. And the claim is that this works for any SK, okay, for any symmetric group, as long as you choose n greater or equal than 2K. Okay? The reason why is because if you want to consider all partitions of size K, the tallest it can be is that if it's all vertical and it has K boxes, and the widest it can be is that if it's all just one row with K boxes. But remember, this all has to sit inside a box of size K times n minus K. So you need to choose n to be 2K so it can fit the horizontal. Okay, and as I said earlier, there's a conjecture that computing these characters is quite hard, and in fact that it's GAP complete, although it hasn't been proved yet. Okay, so one way to understand why this is working is through the celebrated formula to compute characters called the Muller-Nakayama rule. So let me take a step back and kind of, if you break down this computation of the currents and fermions acting on the state, you can kind of follow step by step what's happening. So consider acting with a current associated to the partition 2,1. So I first act with J2 and then I act with J1. So the first step here, where it's goes into these two cases, is J2 and then J1. Okay, so I'm just kind of showing the details of the calculation. And then when you collect the terms at the end of the story, you see that how many times you get this partition and that partition is counting with signs the number of ways of getting to that partition. Okay. So for example, the 0 that we got before came from a cancellation. There are two different ways of obtaining this partition, starting from the vacuum, but they come with minus signs, so the contribution cancels. Okay. So it's kind of like a path integral formulation. Okay, so what is the Murnigan-Nakayama rule? The Murnigan-Nakayama rule tells you that a characters in symmetric group can be written in this way, where this is a sum over something called the border strip tableaus. So I'm not going to describe, but given a tableau, you can define what the border strip tableau is. And then you look at this, that it's basically taking one of these tableaus and filling it with numbers. And then you do some combinatorics, you read off some signs from there. And then you'll see that the signs captured by the fermions are exactly the signs that occur in the Murnigan-Nakayama rule. Okay. So if you want, this what we've discovered is kind of a fermionic representation of the Murnigan-Nakayama rule, where the signs are accounted for automatically. Okay, so if that was the end of the story, I guess things will not be that interesting. But we'll derive this formula by other methods, and we'll see actually similar expressions for these other quantities also. Okay, so one way to see that there's more going on than just a rewriting of the Murnigan-Nakayama rule is the following. So if you have a current, you look at the physics literature, oftentimes it's convenient to define something called a Vertex operator, which is the exponential of the current. And my claim is that actually this is something which is well defined combinatorially, and if you take the exponential, now these new currents obtained in this way, I'm going to compute these so-called Kostka numbers. So define what they are. Okay, so to tell you what Kostka numbers are, let me first tell you what a semi-standard Young tableau is. Probably know, but just to remind you of the set conventions. So a semi-standard Young tableau of shape mu, or corresponding to the partition mu, is a filling of the partition mu with numbers which are weakly increasing to the right and strictly increasing down. So here, 1, 1. Is weakly increasing, then you have to put a 2, and as you go down, it has to strictly increase. Now, the pattern of the numbers that you're putting inside is specified by another partition. Okay, so consider another partition here that has the same number of boxes. So this has 8 boxes, but instead of interpreting it as a partition, I interpret it as giving a collection of numbers. So here, this is interpreted as the number of boxes. The first row is how many ones there are in this filling. The second is how many number of 2s there are in this filling. We'll see there are 2 2s. And then 1 3, 1 4, 1 5, 1 6. Just as filling. So you can fill this shape with a weight given by mu.
It's not uniquely.
No, crucially not uniquely. So for example, you can see here I could permute the 3 and the 2.
Yeah.
It'll be an equally valid filling. Okay.
It's not just the shape that specifies it.
Right. So this is one semi-standard Young tableau. And the question is, how many number of semi-standard Young tableaus there are of shape mu and weight mu? Yeah, and that's what the Kostka number is. Yeah. Okay, so if you want to play around with this a little, you just see that, for example, if you do the same exercises for partitions with 3 boxes, you have these 3 partitions that I wrote before, and if you just count the number of fillings, you'll convince yourself this is
confused about something.
Yeah.
But it had to be the increasing to the right, but you said 3 to the left and 2.
Oh,
And then you said something about switching.
that's wrong.
Oh, okay.
Yes, yeah, so sorry, this is wrong. So this 2 should be a 4, for example, and this should be a 5. Yes, yeah.
And then how?
I messed up with the example.
But I'm confused about your answer to Victor's question about it not being unique.
It's not unique. So, okay, maybe this example, I think even this example, they're probably, yeah, I could put I could switch if I switch the 2 and the 3, I think that'll be correct, right? That'll be a correct filling.
Yes.
Okay, and then with the correct filling, I think I can still flip the 4 and the 5. That'll be correct.
Note that it wouldn't be increasing to the right. But
Oh,
maybe you could
sorry,
swap the
you're
5
right.
and the
Yeah,
6. You
maybe.
could swap the 5 and the 6.
Yeah, that's yeah. Sorry, bad example, last minute example.
Okay.
Yeah, but indeed, so there are multiple ways of doing it. The Kostka numbers capture. Okay, so in particular, they're all positive integers or non-negative integers. Okay. So now, so take these currents associated to integers k. So these are the basic currents, not associated to partitions, just to integers. And consider taking the exponential of this linear combination. So introduce an auxiliary parameter t. Okay, and take the linear combination of these currents weighted by t to the k. And for convenience, I'm going to define things with normalization 1 over k. That will be, you understand later why. But for now, it's just the finish. So this is a function in this auxiliary variable t. And if you expand the exponential powers of t, and you collect all the operators that contribute to a certain fixed power of t, you'll find that there's some operators t hat, which are linear combinations of product of these j's. Okay, so there's no like very beautiful final formula for this. It's a complicated calculation, not complicated. If you're doing a couple of examples, you'll see. But the important thing is that what you get now is a collection of new operators, and I call it t hat, p, where the interpretation, the meaning of the action on the spin chain is that some operator t hat k or p moves a fermion by k units, so same as before, but not directly. So whereas the j's just take one thing aside I and send it to I plus k.
And we're back. Yeah. Got it. But the video is still on video.
Oh, the video.
All right.
All right. Okay. So all right. So now that you have these operators t hat p, t hat k, now I'm going to associate to any partition. I'm going to again associate the product of these t's. Okay. Now the claim is that again, this ordering doesn't matter because these t's are functions of the j's and the j's commute, so the t's also commute. Okay, now if you do the exercise of acting with these t's on these fermionic states, so it's very simple. You just get one fermion, for example, here, try to move it 3 units, but only if there's nothing obstructing it. So if you start with a vacuum, which is 111,000, this only carries the last fermion, so you only get one state. You get one solution. And so you recover exactly these Kostka numbers. Okay. And this one has been shown to be. Okay, so to summarize, what is it that we found? We found that the experimental observation is that if you take a 1D spin chain, you construct these Bethe operators, and then that leads to these currents, which are commuting due to the quantum integrability of the system. You can also define, by taking the exponential, the vertex operators, you can also define these operators, t hats. Okay, and my claim is that these operators commute, and they compute these non-trivial quantities. So if you start with a current J, you act in the vacuum, you get the characters, and if you start with the T, you act in the vacuum, you get these Kostka numbers. Okay. So an actual question is, what would happen if you replace this vacuum state by an arbitrary partition? And then you'll see that what you're computing is something called the skew characters and the skew Kostka numbers. Okay. So it works out very nicely. So this is all quite mysterious at this point. Why is this working? So the question is, what's going on? Okay. So I want to explain the rest of the talk to explain why this works. Okay, so like I said at the beginning, this is explained by the theory of quantized symmetric functions, which I'll explain soon what it is. And more generally, I think of it as a kind of an organizing principle that lets you construct operators acting in the Hilbert space of, in this case, the XX spin chain, which capture interesting data. Okay, so let me review first what the classical theory of symmetric functions is. And so a symmetric function is a formal power series. So consider an infinite set of variables, x1 through x infinity. So it's a formal thing. And a symmetric function is a function with a fixed degree. You're going to consider functions with fixed degree, which are completely symmetric under permutations of all the variables. So that's a symmetric function. This is a symmetric function of degree 2. And this is also a symmetric function of degree 2. That's all. Get data. So the connection through spin chains will come through that each one of these variables xi will be associated to one of the sites of the chain. Okay, so now the claim is that any symmetric function of degree d can always be written. So there exists a certain basis b, which is labeled by partitions of b. Okay, and any symmetric function of degree d can be expressed mostly in that basis given by a linear superposition of some coefficients, which depends on what you're working on. But say you're working on the complex numbers, so these are complex coefficients. This is some basis set for your symmetric functions, and the sum is over all partitions of B, where B is of degree. Okay, so a different basis you can choose, but there are like 5 canonical famous bases. Okay. So here they are. So there's the complete homogeneous basis called H. There's the elementary, which is easiest to define, E. There's a power sum basis P. There's an M monomial basis M. And there's a Schur basis S. And there's something called literally called the forgotten basis, which everybody agrees is uninteresting. But who knows? Maybe it will redeem itself at some point. Okay, so the connection to spin chains is that each of these bases of symmetric functions will correspond to different bases for the Bethe operators. So the J's that we saw before correspond to this basis of H, and the P's will correspond to the T's. And what we're doing when taking the exponential so on is going from one basis of symmetric functions to another. Okay, so this will become clear. Okay, so let me describe what this complete basis is. I'm just going to need 3 bases: the complete, the power sum, and the Schur basis. I'm going to forget the other 3. Okay, so how does this work? So consider first, before considering a general partition, consider a partition that is just a single row with R boxes. So to this partition, you associate this R boxes, which is just simply given by kind of the sum of the products symmetrized over all the variables. Okay, and you allow for repetitions. Okay, so here, these two indices can be the same, so you can have like x1 squared, x2, and so on. Okay. Okay, so then for a general partition, you associate an h lambda, which is simply given by the product of the corresponding function for each row. Okay, this is the definition of what h lambda is. Okay, so for each row, you construct that function, and then you take the product of all rows. So the degree of the function will be the number of boxes in the partition line. Okay. Okay, so the claim is, and this is one of the basic theorems of theory of symmetric functions, is that this set of symmetric functions constructed in this way form a complete basis for symmetric functions. So any function of degree d can be decomposed in this way, and the decomposition is unique. Questions? All right, let's go to the next basis, the power sum basis. So the power sum basis kind of defined similarly. You again get a single row partition with r boxes. Associated to that, you define this symmetric function p sub r of degree r, which is given simply by the sum of the rth power of each variable. So no cross terms. Okay, very simple. And then for a general partition, you define the same. The power sum function associated to lambda is given by the product of each row. Quite simple. It's also a complete basis, so any symmetric function of degree d can be decomposed in this way. These coefficients gamma, of course, will be different from the coefficients they call beta earlier. Okay, so those are very simple to define, but everybody, or many people agree that the most interesting basis is the sure basis. Well, let me tell you about the sure basis. So a sure basis is the following. So instead, given a partition lambda, you want to associate some basis in S lambda. But instead of breaking it down like row by row, where you're kind of not really explaining the whole symmetry of the Young tableau, you consider the Young tableau as a whole. Okay. And instead of breaking it row by row, and the sure function associated to lambda can be defined as being the generating function of the semi-standard Young tableaus associated to that partition. I'll explain what this means. So, I mean, let's say, for example, what this means is that this is given by a sum of monomial terms. Each monomial is associated to one of these fillings of this shape lambda. Okay, that is a semi-standard Young tableau. Okay. So each one of those fillings you associate a monomial, you sum over all of them. So for example, here we got the numbers right. So for this partition, if you have, say, x1 and x2 variables, how more variables, let's say x1 and x2, then this is a correct filling. And then I associate the first term, I associate x1 squared, x2, and then x1, x2 squared. Okay? And then summed over all the other variables as well. Okay. So that's how you construct the sure basis. Okay, so they're all valid bases, the complete homogeneous, the power sum, the sure basis, the monomial, and the forgotten. And they're all valid bases. Okay, like I said, the sure basis is often considered the most important because it's the one that appears in the most diverse areas of math. So, for example, if you look at the sure functions, they are actually characters of the general linear group. So if you look at tensor representations, finite dimensional tensor representations of the general linear group, they're specified by a partition. And if you take the trace of these elements and you express it in terms of the eigenvalues of this matrix, X, G, L, N. So eigenvalues will be x1 through xn. You're going to get a polynomial that's exactly the sure polynomial. That's the claim. Okay. So remember, GLN is a Lie group. So it depends on continuous parameters. Call those parameters xi. And when you take the trace, you get the sure one. Okay, so it relates to the representation theory of the general linear group, and also relates to the representation theory of the symmetric group via something called a Frobenius map, and these are like Schur-Weil duals to each other. Okay, so they also appear Schur polynomials in algebraic geometry, and there's a one-to-one correspondence between Schur polynomials and elements of the homology group of Weierstrass-Meinung. That makes any sense to you, but it's a fact. Okay. So we also see that indeed this basis, which is considered so fundamental, is also the basis is basically the canonical basis in the study of spin chains. The canonical computational basis is a sure basis. That sounds like. Okay, we'll get to that. So before we get to the relation to spin chains, let me tell you about one of the basic problems in the study of symmetric functions, which is if you have a symmetric function in one basis, how do you rewrite it in another basis? Okay, so I'm going to focus on in particular, two changes in basis. So everything related to the sure basis, because that's a nice choice. And then how to go from the H basis to the S basis and the P basis. Okay, so the claim is the following: the power sum basis, if you decompose it in the sure basis, you get some integer coefficients, which are exactly characters of the symmetric group related to the size of the partitions in line. Okay, so that's one of the major results of the theory of symmetry. Characters are the matrix change of basis between the power sum and the sure basis. And the Kostka numbers are the elements of the matrix change of basis between the sure basis and the complete homogeneous basis. These are all classic results in the theory of symmetric functions, which I'm not going to prove here. Okay, so you can relate, there are all sorts of relations in the different bases. They all compute interesting things, okay? And they're kind of related. So some of these guys are inverses of each other. Okay, so a lot of the power of the theory of symmetric functions comes from the fact that in addition to having a linear vector space structure, which is what we've used so far, any function can be decomposed as a linear sum of symmetric functions, and multiplication by scalars, it's symmetric function and so on. They have also the structure of a ring, meaning that the product of two symmetric functions is also a symmetric function. And so it's interesting to look, if you look at that multiplication between elements of different bases, you can always, because this is a symmetric function, you can decompose it in any basis you want. And if you decompose it with respect to the sure basis, you'll find that what appears here are these things called the skew sure characters. So the special case when nu is the empty partition, these are just characters of the symmetric group. And when u is not the empty partition, it's something called a skew character that has to do with the skew shape rather than a. Okay, then if you take the product of H with S, you decompose, you get the skew sure character. So if you take the skew Kostka number, and if you take the product of two sure functions, you get the coefficients here called the Littlewood-Richardson coefficients. And the claims that these Littlewood-Richardson coefficients are the Clebsch-Gordon coefficients for the general linear group. So if you take polynomial tensor representations of the general linear group, you take the product is a representation, you decompose it in terms of the reps, the coefficients are going to be exactly the same coefficient. And the reason for this comes from the fact that I told you earlier that the sure polynomials are the characters for representations of the general linear group. So this will be the problem in the presentation of the general linear group. The product of representations, decompose it, these are called Clebsch-Gordon coefficients, usually for SU2, but for TON. If you take the trace of this equation, you find this. That's a relation. Okay, so the curious relations that we're relating to the P basis to the S basis and the H basis to the S basis are special cases of this example where you take mu to be the trivial partition, because in that case the polynomial is just one. Okay, so we need to look at these are more general relations. Okay, so that was a small detour into the theory of symmetric functions and what does it have to do with spin chains. Okay, so remember what we're trying to explain is this kind of observational fact that we found that these operators J's and these operators P's commute these characters in Kostka. Okay. And these are operators in the Hilbert space of the spin chain. Okay, so to explain that, I'll take the theory of symmetric functions and gonna quantize it so that symmetric functions are not functions anymore, they become operators in the Hilbert space. Okay. And these operators in the Hilbert space will be exactly the operators that we found earlier using the Bethe. Okay, so there's a more general story, which is called symmetric functions and non-commuting variables. It's a big field of math. That's how it's called. Some people call it non-commuting symmetric functions, but that's a bit of a misnomer because symmetric functions themselves are commuting. They just depend on non-commuting variables. So the basic idea is that you have some variables xi, like we had before, you promote them to something called an xi hat, which are non-commuting. Okay. So it's an old story. There's a very nice book by its authors. Okay, so you promote these variables to non-commuting variables, and then to each symmetric function, you associate a corresponding symmetric function that depends on these x hats. Now, because these don't commute, you have to give some ordering prescription, and a lot of the art goes into deciding what are good ordering prescriptions that have nice properties. Okay, so here's one choice, which is made by these authors in 1998, where you take these variables to be, even though in general they're not commuting, they're kind of non-locally commuting. So if they're far apart enough, then they do commute. Okay. And if they're close to each other, if they're nearest neighbors, they satisfy this algebra, which looks a little bit like the braiding algebra, but not quite. So the claim is that this is an algebra I'm going to call it the Foreman and Green algebra, and it contains a couple of different algebras of special cases. Okay. These are widely studied algebras. Okay, so this seems a bit arbitrary at this point, why you assume that the x hats satisfy this algebra. But something nice happens if you assume that. So, okay, to see that, what do? So we take the complete homogeneous functions HR. I can associate to that an operator h hat of R, which is going to be defined in this way. So remember the HRs without the hat were defined by the product of these x's, and they were allowed to be equals. Okay, in the case in which all these variables commuted, the order didn't matter. Now here the order matters, so I've been careful here to write it in a sort of order, which is kind of increasing to the right. So here we put the variable with the largest index and then going down to the left. Okay. So you can choose whatever ordering you want, ascending or descending, but you have to be consistent. So this is the definition of what we mean by the h hat R's. Okay. Now the claim is one of the theorems by Foreman and Green is that if the x hats satisfy the algebra that we wrote before, then these h hats actually commute. Okay, so even though they depend on non-commuting variables, as a package as a whole, they commute with one another. Okay, in fact, that's one way to. So demanding that that is true leads to the algebra that we wrote earlier. Okay, so say you want to impose these. Okay, so now to a general partition, you associate, and this is all kind of standard work in theory of symmetric functions, non-commuting variables. You define the h hat lambdas in the same way that we defined the h lambdas before, because these guys commute, this order doesn't matter, and we can define these. Okay. So this should remind you of the Bethe operators that we started with at the beginning of the currents. Because the Bethe currents commute, the order doesn't matter, and they're specified by Vertex. Okay, so that's how you define the h functions. Now, the short functions, if you remember, they're defined as generating functions of the semi-standard Young tableaus. Okay, and that will still be the case, except that now the variables that we're putting inside 1, 1, and 2, and so on, now they're kind of non-commuting, they're associated to non-commuting variables. So, but the definition is still, strictly speaking, the same, but you have to be careful with the ordering of the terms here in each one. But to give the same example as before, here we had x1 squared x2, and here we had x1 x2 squared. Here we have to be careful with the ordering. So you start, depending on the conventions, but you go from each row from left to right. So from the bottom up and then each row. So you do x2, x1, x1, x2, x1, x2. And that's the ordering together. Okay. So that's a prescription. It's an ordering prescription on how you define the short polynomials. Now, with this ordering prescription, the main result of Foreman and Green is the following: that the s hat lambdas commute with one another, and they also commute with the h's, provided the x's satisfy this Foreman and Green algebra. Okay, so you can make these functions or polynomials and non-commuting variables as a package with the correct ordering. They commute. So what that means, one of the applications in particular, is that any classical relation that involves only h's and s's that holds classically also holds in this case of non-commuting variables. Okay, because all the manipulations that you did classically will carry through, because the only thing that could not hold true is that something doesn't commute. But if it involves as a package the h's and the s's, you can be sure that that relation will hold true. Okay, so just now it seems like you introduce all these non-commuting variables and then you package them into something which is commuting at the end. So what did you gain? Right? It seems like we just kind of went backwards at the beginning. Okay, so you do gain a lot by doing this because this is a completely different representation of symmetric functions. And there's one in particular representation that connects to the spin chains, and that's what one. Okay, so consider this semi-infinite chain. Okay, so yeah, this corresponds to having potentially infinitely many variables. And now for each site, I'm going to associate the operator, the operator x hat I, which is given by this. Yeah, we had a quick stop. All right. Okay, so these operators. So I'm going to choose the x hats to be given by this. These hopping operators by 1 unit, where these a's are fermionic operators. So you can check that this actually satisfies the Fomin-Green algebra. So it's a fermionic representation of it's a particular representation of the Fomin-Green algebra in terms of fermions. Okay. Now what you can see when you make this choice is that these operators H hat are precisely these Bethe operators that shifted all the fermions to the right by R units, provided there's nothing in between. And this is basically comes from the definition of the H hat, because the H hat is like the product of all these x's. And each x tries to move a fermion to the right 1 unit. The product of all these x's moves all the units, all the fermions step by step. So in fact, these are exactly identical. So remember, these are the operators you obtained when we took the exponential of the current. Okay, in particular, the Hamiltonian is basically the shift by 1 unit of the fermion chain. And in this language, then the Hamiltonian of the x-axis spin chain is the symmetric function, the complete homogeneous function associated to the partition with 1 box. Okay, so the Hamiltonian is the operator with 1 box sitting at the bottom of the Bethe tower, and all the higher partitions with more number of boxes are on the side. Okay, so I told you that the Schur function will be kind of crucial. Sorry, the Schur basis will be important, and that is seen as follows. So if you take one of the Schur operators, I'm going to call it operator from now on because it's really operating the Hilbert space of fermions. If you act with this on the vacuum state, so all the fermions cramped to the left, and you act with them with the Schur functions, you see that this thing exactly creates. There's just one term remaining on the right, and it creates exactly the state associated with this coefficient. Okay. So in other words, the Schur basis, the staircase, when we chose the staircase representation, that corresponds to choosing the action to create the states using the Schur operators. Okay, so this is very close to explaining one of the relations we found at the beginning. So remember that the relation change of basis between H and the S involves these Kostka numbers. That's a classical relation. It also holds in terms of operators, as they argue, because this H hats and S hats commute. So this relation is true. Now, if you take this equation and act with it on the vacuum, you see that this acting in the vacuum, that this gives you a linear combination of these guys acting in the vacuum, it just creates a state lambda. And so this is exactly, in fact, the observation we found. So remember, these were the action of the T's. We took the T's, we act with them on the vacuum, we created this table of Kostka numbers. So this explains that the reason why that worked was because the operators T's that we constructed by taking the exponential of the currents created this Kostka numbers. And this is the reason. Okay. Okay, how about the character formula? So the character formula, just the intuition is that it should similarly follow by a relation like this between the P's and the S's, which is a relation change of basis between the power sum of the Schur functions. Now, Fomin and Green don't tell you what these P's are. They only talk about H's and S's. Okay, but there's a way to find what these P's are, and the argument is basically the following. So, okay, so it's useful to introduce these classical generating functions. So you have the classical functions h sub k, define the generating function which collects all of them into the capital H, and for the power sum, this is 1 over k is conventional. This is the generating function for the power sum base. And there's a famous relation, well known, which is if you take the exponential of the psi, you get exactly the h. Okay, so this is a formula that actually Newton figured out in the 1700s. Crazily enough. So to be more precise, the Newton identities are identities between the h's and the p's, and all those identities are encapsulated in a single equation given by this. Okay, so this is called Newton. Okay, so now the point is that we already know what the h's are, the quantized version of the h's. And so what I'm going to do is I'm going to define a quantized version of the power sum function psi hat given by this relation. I'm just going to declare there's a generating function psi hat for the p hats, which is given by the logarithm of the quantized function for the h's. So that would give a bunch of relation between the p hats and the h hats. If you want, I could just define it that way. This would be the quantum Newton identities. Okay, so putting things together, basically what you find is that these p's are equal to the j's. If with this definition, the p hats are exactly the currents that we found earlier. Okay, that explains the reason why we normalize things with this 1 over k earlier like this to construct the t's. What's that? So that this what exactly works. Okay, so current operators, and the reason why current operators were capturing the characters of the symmetric group is because they identify with the power sum basis, and the power sum basis related to the short basis captures the characters. Okay, so in fact, we can derive a bunch of other formulas, not just the first two that we observed, but if you take these general range structure relations for symmetric quantized symmetric functions, now all these relations holds because we define what the p's are, they commute with one another, and with the s's and the h's and so on. All these relations hold. And in particular, if you act on the vacuum, you get all these relations. Okay, so the first two explain the two observations we made earlier, but you also find a way of computing Littlewood Richardson relation. This club's coefficients. Okay, so basically all these coefficients are understood as transition amplitudes of symmetry operators in these spin chains. Okay. All right, so that's kind of the main result. So just to summarize, symmetric functions and quantized symmetric functions explain the algebra of Bethe operators in quantum spin chains and explain the appearance of all these different functions. Okay, so now this is kind of more open for discussion, but I want to suggest that if you look at, well, we had the book by Richard Stanley there to get to my attention. If you open the canonical books on references on symmetric functions, you'll see that short functions are kind of the most basic, functions. You can define different generalizations called Schubert, the Grothendieck, and so on, power generalizations. All Littlewood, McDonald, double Shor, supersymmetric Shor, etc. So many different functions you can define. And you may wonder if these actually appear in quantum systems. So the Shor functions appear in the XX spin chain. And it turns out that actually they do. So if you look at so far here, we've looked at the first two lines here. So if you look at the XX spin 1/2 spin chain, that relates to these coefficients that we discussed, they have this complexity. If you look at, for example, each spin, instead of being a half at each side, you allow it to be dimension d, you'll find the Schubert polynomials. The Schubert polynomials are controlling that spin chain. If you look at the XXZ spin chain, so in terms of fermions, this will be introducing a quartic interaction among fermions. This relates to the computational Dromov-Witten invariance, whose complexity is completely unknown as far as I understand, but you probably don't know what Dromov-Witten invariance are, so just ignore that. And if you look at these other more complicated functions, they also appear in higher dimensional systems. Rather than, instead of 1D, they appear in 2D and 3D and so on. Okay, so going back to the beginning, basically the program that I'm suggesting is, within the space of quantum integrable systems, there are different systems with different amount of structure and interaction and so on, and they compute different quantities. We've just explored this block here that relates to the XX spin chain, but it will be interesting to understand what kind of to chart out the complexity of the different problems that arise here and see exactly how this comes by the quantum advantage processes. That's what I'm proposing. Yeah, so I'll leave it there.